For our very first cube, we had to choose two materials. So we chose plastic and elastic. The reason we chose those two materials is because of how contradictory they are of each other. So plastic is, through natural environmental conditions, it stays very tough and strong. However, elastic is very malleable and can easily be altered with a small force. So first we began designing our cube using our two materials in harmony. We did not use any adhesive in our design and wanted our cube to hold purely by forces. So first we used the nylon cords to create inward forces inside the cube, and for the plastic to resist those forces, we created this jigsaw puzzle that not only allowed us to keep all the forces balanced, but also allowed our dimensions to be as accurate as possible.
Okay, so our second corruption is denser, and we borrowed the idea of submarines, and so we know that the glass back density is 1.1 while the water density is 1, so we need to mix different density together to make this thing floating in the water. If we make it solid, it will definitely sink into the water, so we make it hollow, and these two tubes are hollow while we suit the other tubes, and we leave a little hole there so we can control the volume of the water get into it. So we can control the heaviness of the whole tube. So yeah, this is the video of it floating. Yeah, and the technique is to use this roll. We put the glass bags on it with the baking paper, and we use the roll to roll it.
This is our second cube, and the corruption is hotter and colder. In this version of the cube, we played around with the idea of thickening weaves and making new weave patterns. You can see that this one is sort of centralized, and here was our first attempt to have like a three-dimensional weave that increased the thickness of the weave pattern. And we created these images that show a visual pattern of how the thickness of the weaving correlates to the temperature that goes through, or the heat that is allowed through, and from the center heat source there was a pot with a candle inside. So you can see that as we turn the cube, the thicker and its thinner sides show more or less insulation, and it's quite clear in this visual pattern.
Mechanism. If we now look at how our structure failed and where it failed, we have to keep our eyes on the back, where we can see the weight and a water bottle on top of it. And we have to look also at the connection between the truss and the main platform. Now, as Davide adds the last 500 grams with a half liter of water, we're going to notice how in the back, the string, which is under the counterweight, is going to go in strong tension, putting the counterweight in balance, lifting it a little, and we're going to see the big liter of water fall over. This gives less counterweight, and the platform starts dipping forward. The bottles fall, the shock breaks the connection between the trusses and the main platform. The whole thing results into a failure of the structure.
The structure uses the funicular system and is created using resin brushed over suspended cloth to create a solid entity. And therefore, this makes it stable because there is no joinery or weak points. However, it failed because under external force, it stretches due to its elasticity, and therefore it does not break. There was cracking that could be heard in the video, but that only occurred after it had gone over the set constraints.
Wait. That's 2, 3.
Look at the bending. No, before you continue, look at the first beam.
Be careful, be careful.
Look at you see the buckling? What do you see?
So how much load? How much load is it up? 4. 4 kilograms.
How many to take?
You need to take 12.
Oh my god.
So that's 5. 6.
Look at that.
So you're broke in the middle of your trusses.
As our structure had to be a funicular, the form had to follow the force, so we began to look into arch systems in churches, predominantly the way they behaved in compression. We looked at the buttress systems outside the church and began to make models employing both arches and vaults which would spread the load and remain stable while in compression. In the final model we took forward these ideas of using systems that are similar to churches and designed a structure that would, with the use of various arches, spread the load throughout to different points where the structure would touch the ground, where each arch system was then pinned together at the bottom. This pin and tie system remained in tension under the weight or force from above. By pinning it at the base, it meant that the legs would not move outwards and they would stay stable while the load was applied. One might argue that our structure was in fact too stable, as it supported well over 4 kilograms without failure. However, this meant that it did not adhere to the criterion A that specified it failed before 4G. I think this stands testament to the effectiveness of the funicular as a structural element. The funicular also allows for, similarly to our model, a high weight to strength ratio.
So this is group 1H, and for our initial cube, we chose leaf as our base, as a material.
We chose this material because we wanted to have something that was environment friendly and cost friendly as well, and would be an easy material to manipulate. We could play with the material as much as we could and make more experiments because of the way it is.
And of course the season was really perfect for this material, so we found a lot of leaves. So basically the method we chose was a papier-mâché method, but with leaves. So we made 5 sheets of leaves, and we cut them in a square, and then we stitched them together, and we put leaves inside so it keeps stand by itself, and we don't have a frame.
So this cube is the corruption is to make it more bendier and more elastic. So our material from our previous cube was plaster and blue foam, and so that's what we're working on. And
actually, it was original blue foam, original cube is this. The way is this way, but we changed it. The tool, we have a gap, and then we change it the way. So
then we can see that it's when you put a heavy object on it.
So
it twists.
Yeah, it twists, and then it works better than before. So that's our bendy cube.
So the last corruption was to make the cube darker and to use only waste. So we calculated the remaining waste that we had, which was 21.5 meters of balsa wood. And we compared it to the whole surface. To cover a whole surface, we needed 36 meters, so we had to find another solution. Plus we had the pulley weights that we could use, and we imitated the waste of the paper on which we printed. So we inspired our design from Japanese cranes, and to create a dynamic light movement, we used the pulley weights aligned. So when the light moves over it, it creates like a musharabia effect in the Arabic architecture. And so we had several tests. One was only with a dark cover, and it was too dark, so we changed, and the daylight factor was reduced to 2%.
How did it fail?
We think it's gonna tilt forward and these are gonna snap, so it's gonna come right at you.
Sorry, what? Thank you, thanks for telling. What do you think is gonna snap? Sorry?
Yeah, the ones in the back.
Probably. Or back. Okay.
Or it might like twist. It's quite unpredictable. It's quite about right.
I'm really glad you guys have thought this through yourself on this. Halfway there.
More on the right.
Our first model consisted of 3 column trusses and 2 platforms. One platform to connect the 3 trusses together, and another a loading platform that was suspended from the top of the trusses with the use of string. Our prediction for this model is that it's going to snap either in the lower platform, as it's divided into 2 parts to make it weaker, or the strings that are holding the loading platform at the top are going to break. As the weight is being applied, the loading platform immediately glues to the lower platform. The strings are working in tension, while the loading platform is compressing the lower platform as the weight is being applied. As the weight continues to increase, the lower platform starts to deflect, causing the column trusses to lean towards the center. The model experiences extreme deflection. At 9 kilograms, the model breaks. As expected, the lower platform breaks in half. Our design is composed of 5 structural frames assembled in a decreasing linear manner connected with one centered beam on the top. At the center of the beam, a floating cage is found that is composed of 3 suspended vertical structures that carry the beam grid platform. The structural frames are braced all together at the bottom. The M shape of how the frame is sloping down is an added value to be aesthetically pleasing. Our previous model failed at the 5th bottle, 2.5 kg, due to the imbalance of the weight distribution on the platform. This is because the platform is held by 3 vertical wood structures rather than 4. Thus, when the pressure is applied in the middle of the platform deviates downwards on the side, with the 4th support missing. This in turn leads to the opposite side snapping.
Yes, this is our original cube, made of iron filler and resin. Actually, we make a first 30 by 30 wood mold and put lots of resin and iron filler. The weight of this cube is exactly 22 kilogram, and it was the first time I cannot remember exactly, and we did not report that. We poured around 15 kilogram of the iron powder and 7 kilogram of the resin. So this is what it made for, and yeah, there are some gaps.
Also, there is a wooden structure inside to support the main cube.
Because the process of basically making it has to be done in layers, because resin and iron are quite dangerous. So we had to make another smaller mold in order to use less iron and resin, so there was the waste material.
So that's how we made our first cube.
So our second alteration for the cube was to make it much lighter. Our first cube was, since it was a solid of marshmallow and popcorn, it was very heavy. So for us it was a big challenge to try to make it as light as possible. So we thought about different ways of trying to achieve this. So for that we thought firstly that we should make it hollow to avoid using as much material, therefore avoid having extra weight. So we thought firstly to kind of use a balloon inside to keep the air and the shape of the marshmallow, but as you can see it didn't really work out very well, since when you heat up the marshmallow heats the balloon and it expands. Our second trial for this was to make it out of paper, but in a smaller scale it works, but when you make it a bigger scale, the 30 by 30 by 30, the marshmallow is too heavy so the paper cannot hold its shape. So lastly for this we thought about making it with foam, which is a very solid structure when made thin, and we managed to achieve from a 12.2 kilogram to a 1.55 kilogram result.
Our corruption is soundproof, and we decided to make, our test pieces were a 10 by 10, 6 different faces of 10 by 10, and we essentially use it as a box within a box. So we used all of our test pieces, and they are inside here. And then there's also wood chip inside to kind of insulate the sound. And let's just start. So it's considerably quieter. It's not silent.
And we're supposed to add more wood chip over it.
But we'll save your office.
The design consists of 16 bend-active copper arches. The inner 8 arches are completely vertical, and the outer 8 are slightly slanted inwards to stabilize the structure and to cope with perpendicular forces. The slender copper arches make the top platform seem to float. The copper wires were bent, and thus their ability to be compressed was hindered slightly. This was a slight move by us to adhere to the failing load before 14 Newton, which it did. The copper tubes were very thin, and thus as the weight neared 36 Newton, they began to bend under the amount of weight and compression, meaning that the platform leaned forward, allowing the water bottles to roll off. This was how we expected it to fail, as these copper tubes were the weakest part of the design when under pressure.
2, 3.
It kind of works in 4. wait, stop. So it kind of stands at 4, so let's see how many more it can
That's
do.
5? I think it's about...
I think it's 34.
How many?
It's interesting to see how important it is to load symmetrically. As soon as you have a symmetric load, everything crashes before. Okay? How about the deflection?
About to tip over.
Yeah, put your hand. It's okay, let it fall.
There it is.
Good.
About to tip over. Yeah, put your hand. It's okay, let it fall.
We decided to stick with our previous design for the small model and wanted to work with the grid with reinforcement in the inside to prevent deflection, but we wanted to make it cantilever to give the appearance of floating. This is the model we ended up with. To make it fit within the box, we made it out of 16 different pieces of MDF that we assembled with bolts, and in the back we added reinforcement with wires to create tension to prevent deflection of the two legs. But our mistake here is that we should have added one on horizontal position to prevent deflection and buckling. As we start loading our model on a plain surface on a table, we already see that the legs are shaking. In fact, the material is too weak and they're not standing properly because in fact, again, we would have needed one wire to connect the bottom parts of both of the leg to add tension because in fact here, the two cables are not in tension, meaning that they are not really used to their full potential. At this point, you can see that the left leg is already starting to buckle. However, our beam grid is still standing properly and not buckling nor being bent. We slightly tried to hold the legs, but in fact the right leg broke before we could see it. In fact, on the smaller models, the legs in MDF were shorter, so they performed better when carrying the weight. As a conclusion, the legs were buckling because of the weakness of the material. Also, it failed because the force created compression on the legs, so bending happened, which caused the model to break.
So for the fourth cube, the corruption was faster. First of all, we sped up our process by laser cutting the molds for speed and accuracy. We tested sheets of MDF stacked together, finding out that they come out easily because the water from the plaster saturates into them. We went with the process of having two lids, which everything fits inside, with inset parts that columns then slot into. Yeah, in assembly. The one issue we have in this process is due to the crumbly nature of it. Every time you do it, it becomes harder the next time.
Alright, so because our third corruptions is more about stability and how it's gonna create that illusion of floating in a way that there isn't much support underneath. So we are thinking like, should it be just an egg or many different eggs together? But we finally came up with an outcome to make it challenging for us in a way that it's only supported by one egg. And what you can see here is that this form is actually acting as a structure that kinds of hold together but not doing any kind of supporting in terms of gravity. So it creates that illusion of floating effect. And
so our second corruption was to make the cube twist, and as already our material, that's the foam, we know that twists a lot. We did at the beginning 10 different small models to try and find the one that twists the most, and we realized that all of them actually twist a lot, especially in a small scale. And so at the end we decided to choose the one that also by the design looks nicer. When we did it in a bigger scale, the twisted wasn't as much as the small one, but still, because when we chose the cube, the final cube, we realized that we are gonna have two different angles because we cut it and we made horizontally cuts that tells us exactly what to do. So the first layer twists by 25 degrees, while the third layer twists by 30